All right. Okay, let's get started. First off, I want to apologize again about the confusion on homework 3.4. I think I know what happened. When I picked the problem, I think I pulled the textbook off my shelf, and I just pulled the last edition one because I taught. This is my third time teaching this class, and so we went to a new edition in between me teaching it, and I think I just assigned the problem from the old version, not the new version, because I started getting questions from students who said, okay, you gave us some hints, but I don't really get the hints. I get the problem, but I don't get the hints. And I went, well, that makes sense because it's the wrong problem. The original, what had happened is the original problem was very similar. It was just a different geometry, and the dimensions that the book gave for that problem weren't totally clear. This dimension being 10 inches, this one being 20 inches, or something like that. So what I was doing was trying to explain how you could compute the coordinates for some of those points, but then I think because the problem didn't match, the hints were even more confusing. But when I looked at the problem, I said, this problem's fine, so we'll just keep going. We'll just roll with it. So my apologies for that. Right now, so I know homework 3.1 is graded. That should be visible right now. The 3.2 and 3.3 are being graded. I think that 3.2 is pretty close to being done. I will check that sometime today. And 3.3 just got turned in. But these solutions should all be available, and you all just turned in 3.4. So 3.5 will be assigned today, due Monday. And we are actually rocking and rolling in the land of rigid body systems and moments, because we're starting to approach sort of the pinnacle topic of this unit of the class, which is how to deal with equivalent systems. And so we're getting there, and today I think you'll sort of see the light at the end of the tunnel, as it were. Okay. Now, to sort of explain that light at the end of the tunnel, let me sort of go back to the last unit of the class to sort of explain what we had done in that last unit and how there's some very strong parallels to what we're doing now. So the first unit of the class was all about statics of particles and adding vectors. So we really sort of had three tasks. So the first thing that we had to do was learn how to describe vectors. And so we learned that graphically and trigonometrically, and then we delved into IJK notation. And then the second phase was to learn how to add those vectors together. And ultimately what we were trying to compute was what we call a resultant. So the idea is if you have a particle and you have a bunch of forces on that particle, we can replace that bunch of forces with just a single force. That would be statically equivalent. Okay, keyword statically equivalent because it's statics. And then the third phase was static equilibrium. Okay, so now we have a particle that has a series of both known and unknown forces applied to it. What are those unknown forces required to be such that the particle is in static equilibrium? So that was sort of that first unit of the class. And now let's talk about the parallels for the second unit of the class, where we're talking about moments. So for the past few lectures, what we've been doing is describing moments, describing them in 2 dimensions and 3 dimensions, moments about an axis. That's really what we've been talking about, and we're going to do that today with force couples. But then the next step is, what about adding those together? What if we have a system of forces and we resolve those into a smaller system or an equivalent system? And that's what's going to be the end of this rigid body systems unit. And then the next step past that is rigid body equilibrium. We have a system, a rigid body, with both known and unknown forces on it. What are those unknown forces required to be in order to keep the system in equilibrium? We have a name for those forces. We call them reactions. Sort of like, the whole Newton's third law kind of thing. Okay, so let's talk about the formal definition of a moment, just to make sure we're all clear on that. So if we have a force out in space, we say that force generates moment about some point in question by computing the cross product of r and f being the force vector in question, and r being a position vector that points from the point in question to the line of action of that force. And we know by now that we can use oodles and oodles of different r vectors as long as it starts at the point in question and ends on the line of action, and we will get the same answer for the moment. Okay? Because really what defines that moment specifically is its axis of rotation and its magnitude. And the magnitude, it can be determined by taking the magnitude of the force and multiplied by the moment arm, the shortest distance from the point in question to the line of action. So what we're talking about today are what are called force couples, okay? And this happens quite a bit in engineering systems and in physics, but basically a force couple is a pair of forces like this, okay? And so the best way of describing a force couple is we have two forces that have the same magnitude, they have parallel lines of action, and they point in opposite directions, okay? So we have a line of action here, a line of action here. They both have the same magnitude, but they point in opposite directions. These two forces here would be said to, would say to be formed, or would be forming a force couple, okay? And I think by now, and based on the discussion, I think it makes sense why we're talking about this, because if I have a system and I take a force like this and a force like this, and I do that, what's it going to want to do to that system? It's going to want to rotate that system, right? If a force is an action on a body that increases its tendency to translate, a moment is an action on a body that increases its tendency to rotate, okay? And I think it's pretty obvious that this system would want to cause rotation. From a force standpoint, the tendency to translate would be zero because we got a force going this way and a force going this way. So the only thing we have would be rotation. Yes, sir?
Is there such a thing as a torque couple?
As a what?
A torque couple? Like having forces in such a way that basically causes two couples to sort of torque in opposite directions?
That's a good question. I guess technically you could have that. Really, the only time we're going to be interested in that in engineering land is if we're talking about an element under torsion. Because if we have an element and we twist one way and we twist another, we are taking that element and applying a torsional moment to it. So we have to ensure that the element doesn't rotate too much and doesn't cause too much stress. But that would be something you talk about next semester in 216.
Because that does sound like a civics thing. Like some buildings probably could have enough like size to have wind want to go one way and something else underneath want to go another or something like that.
Well, I could talk all day long about wind loads on buildings, and that is all I'll say is in the land of civil engineering, that is a topic in and of itself. Is how we deal with wind. So taller the building gets, the more complicated it gets from a wind standpoint. Okay, any other questions? All right. So in order to determine the moment generated by a couple, we can still use the same definition of R cross F. I think you'll find at this point that really we end up using the same definitions over and over again. What ends up changing from topic to topic to topic is our definition of R. So in this case, R would start on the line of action of one force and end on the line of action of the other. Okay. And as for the F, you could really use either F and you would get the same moment, because both of these forces are generating the same type of rotation. For example, this is wanting to rotate an object, let's say, in a counterclockwise fashion. Okay, now I really want to make sure that I'm hammering the importance of where we're going with this by introducing the concept of what I would call an equivalent couple. Okay, so let's take a look at these three systems. Okay, so I've got a box, okay, and this box is 6 inches wide and 4 inches deep, okay, and with each of these three systems, what I've got is a force couple being applied to them. So for example, over here, I've got 20 pounds down, 20 pounds up. Here, I've got 30 pounds in, 30 pounds out, and here I've got 30 pounds in, 30 pounds out, but this one's applied to the bottom of the box, this one's applied to the top of the box, okay? So I want to talk about what these three systems represent. First off, let's just use the definition of the couple from a magnitude standpoint. We define the magnitude of the moment generated by a force couple as equal to the magnitude of one of these loads times the distance between them, the shortest distance between the lines of action. So in the case over here, we have 20 pounds is our magnitude, and the distance between them is 6 inches. So 20 times 6 is 120. What about over here? Well, we have the magnitude is 30 pounds, and the shortest distance between the lines of action of these two forces is 4 inches. So 30 times 4 is 120. 120 again. Same thing over here. 30 times 4, 120. Every single one of these couples generates the same magnitude of moment about the axis in question. And speaking of the axis in question, let's consider our right-hand rule. Okay, so let's say here's the box. I know it's not a box, it's a tape dispenser. But let's say here's the box, and let's consider this first scenario over here. Okay, so let's see. So we're pushing this way with 20 pounds, this way with 20 pounds. So we're doing this to it, right? So if our thumb is in the axis of rotation, our hand is rotating it this way. So if we're rotating it this way, our thumb is pointing like this. Our thumb is pointing in the direction of the positive y, right? So for this scenario, I could represent this moment vector as 120 times j. And in terms of the units, it would be inches times pounds, or inch pounds. Does that make sense? But that's also true of this and this, right? Because they're both wanting to cause rotation about the same axis. What I am getting at is that for, let's say, this system, instead of having 20 pounds here and 20 pounds here, I could delete those forces completely from the system and just replace them with a single moment vector of 120j. Same thing over here. I could delete this and replace it with 120j. And some of you might think, well, wait a minute, what about force equilibrium? Well, from a force standpoint, I've got 30 pounds to the left, I've got 30 pounds to the right. They cancel out. I can't simply delete them, though. I have to replace them with an equivalent amount of moment. Does that make sense? So I propose that for these three systems, what I am saying is that they are statically equivalent, okay? That all three of them result in the same amount of net force and net moment on the given system, okay? And what we're doing is we're steadily approaching a very, very important topic in statics, which is the concept of an equivalent system. See, what happens is, in our world, we deal with systems that have oodles and oodles of forces on them, that have forces all over the place, okay? And that, to be honest, sometimes is a lot of bookkeeping and a lot of stuff to deal with when we're when we're doing stress analysis and performing our engineering computations and engineering designs. And so a lot of times what we will do is we will take these cases and resolve them into a smaller number of forces that's a little bit more manageable. So instead of these two forces, I'll just replace it with this one. Instead of these two forces, I'll just replace it with this one. Okay? And so what we're saying, and we're approaching a very important topic in statics, is that if I have two systems, system one and system two, I posit to you that those two systems are statically equivalent if the sum of forces in system one equals the sum of forces in system two, and the sum of moments in system one equals the sum of moments in system two, okay? And we're going to spend the next few lectures looking at that, taking large systems with large number of forces and resolving them into a smaller, more manageable number of forces that we can then ultimately deal with later. For now, though, what we're going to do is we're going to kind of do this now, but we're going to do it softly because we're only going to consider force couples, ones that are a little bit more easy to identify. Okay, so what we're going to do today is we're going to focus on this example. Okay, now what we have here is a system or a rigid body that is subjected to a series of force couples. Okay, let me pull up the notebook here to kind of illustrate what we got going on. All right. So I have here a force system. Now, how many force couples can you just observe are present on this system? I've got 3. I've got the 16 pounds, I've got the 40 pounds, and then these two right here, which I'm saying the magnitude is 20 pounds. Okay? So what we're going to do is we're going to deal with each force couple one at a time, okay? What we're going to do is we're going to take each of these force couples, we're going to determine their magnitude and direction, and then ultimately add up each of these force couples one by one. And so what we're ultimately going to do from beginning to end is how many different individual forces do we have applied to the system? We got 1, 2, 3, 4, 5, 6 forces. What we're going to do is say we can get rid of those 6 forces and replace them with a single vector that has that generates the same amount of moment as the collection of all of these. Okay? So ultimately, our goal at the end of the day, if you want to write it like this, our goal at the end of the day is to take the moment, let's say, from the 16-pound vector, or force couple, plus the moment from the 20-pound force couple, plus the moment from the 40-pound force couple, and we're going to add them together. That's how we're going to handle this from a static standpoint. And I think you'll see where we're getting with this. You'll see that that it's quite manageable. Now, I would like to make a note before we move on. So let's make a note before we move any further. Can somebody tell me what this equals? What is the sum of forces on this system? Not the sum of moments, the sum of forces.
0.
It's 0. Or if we want, we could say the 0 vector, right? Because if I have 16 pounds up, so this, like if I wanted to represent this 16 pounds as a vector, how would I represent that 16 pounds as a vector? It'd be 16j, wouldn't it? And this one is going to be 16 negative j. So what's 16j plus negative 16j? 0, right? And if I keep doing that with all of the remaining forces, the same thing's going to happen. Even this 40-pound, this pair of 40-pound vectors at this somewhat oblique angle, we're going to have the same scenario. So in the end, I want you to recognize that the sum of forces equals 0. But by now, I think we can look at this and see, well, the system's not in equilibrium because it's not just the sum of forces we got to deal with, it's the sum of moments. Okay. All right, so by now, I think you know we're going to need some point coordinates. And what I'm going to do, hopefully by now, this is becoming familiar on how to do this. There are 5 points that we need to consider, A, B, C, D, and E. If you're okay with this, I'm going to go ahead and just give you some of these. So, for example, with point A, we don't go along the x-axis, we don't go along the y-axis, but we go along the z, and we go along the z positive 20. So the coordinates of A are 0, 0, 20. And then for point B, we've got 0, 10, 0, because we go up 10 along the y. We've got 30, 0, 0 for C. A, B, and C just go along the x, y, and z axis, so that makes it pretty easy. For point D is sort of like the average of point C and point A. So that's going to be 15, 0, 10. And then point E is like the average of B and C, right? So it's going to be 15, 5, 0. Does that make sense? Hopefully that should be pretty straightforward. Now I'm going to level with you. I'm going to cheat a little bit. Give me 1 second. Because I don't want to scroll up and down like crazy. Let me cheat a little bit. Give me 1 second. I'm cheating. Sorry. Oh, because I don't want to scroll up and down like crazy on this. Okay. Do that. Okay. Microsoft doesn't like me today. Okay. So what we're going to do is we're going to handle these force couples one at a time. Okay. And I'm going to start off with the 16-pound force vector. Okay. I'm going to start off with this 16-pound force vector, and I want to see if there are two ways of computing this force couple. One way involves the very formal definition, R cross F. The other is hopefully a little more straightforward. Okay? Let's start off with the straightforward method. Okay? So let's look at the 16-pound force couple. Okay. I want you to help me out with something. I want you to look at this problem and tell me about what axis does that 16-pound force couple cause rotation. Is it the x-axis, the y-axis, or the z-axis? The 16-pound? The z-axis, right? Because 16 is going up, 16 is going down this way, so the rotation is going to rotate around the z. Does that make sense? Now, the forces are aligned along the y-axis, but it's causing rotation along the z. Does everybody see that? Okay. All right. So I want to let's just observe that real quick. Okay. So rotation about the z-axis. All right. Let me ask you another question. Let's talk about the right-hand rule. Right-hand rule states, I take my thumb and I point it towards the positive z-axis, and my fingers indicate positive rotation. Does the 16-pound force couple generate positive rotation? No, it does not, right? Because if I point my thumb towards the z-axis, my fingers are rotating like this, but the force couple is rotating it like this, right? It's rotating it in the other direction. Does that make sense? Does everybody see that? Okay, so I'm proposing that what I'm saying is that, bless you, what I'm saying is that rotation does not follow right hand rule. In other words, negative rotation. Bless you. Okay. Lastly, I want to ask, what is the moment arm for these two forces? The 16-pound forces. Remember, the moment arm is defined as the shortest distance between the two lines of action. What is that? 30, right? So 30 inches. So therefore, if I wanted, FD is 16 pounds times 30 inches, which is 480 inch-pounds. So therefore, that. How did I get that? It's about the z-axis, so it's associated with the k vector. It does not follow the right-hand rule, so we're dealing with negative rotation, and the magnitude equals the magnitude of one of the forces times 30 inches, so 480. So that would be what I would call method one. So actually, let me cheat a little bit more. So we'll call this method one. We'll call this by observation. That's one way of doing this. Another way of doing this is as follows, and this is probably where my little cheat sheet might come into play a little bit. All right, so you know what? This is getting in the way. I think I'm just going to scroll a little bit. So method 2 is to use R cross F. Okay, now the way that works is as follows. So again, my apologies for the up and down scrolling a little bit. So what you need to do is you need to pick a point of reference, okay? So when you're performing the cross product, what you need to do is pick one of these as a point of reference. I'm going to go alphabetical, and I'm going to say that this one right here, that's my point of reference. So what that means is that my R vector, that's going to be R, and this is going to be F. Okay? That's going to be R, and that's going to be F. Now, I could very easily pick this as my point of reference, and if I did that, then this would be R, and that would be F. It doesn't really matter. You'll get the same answer. And you'll see what I mean here in a second. So, in this case, what is F? Like if I needed to define this F vector, what would that be? What direction does it point? Like what axis? The y-axis, is it positive or negative? Negative. So this F vector can be represented by negative 16j, right? And as for the R vector, what I do is take the coordinates of C minus the coordinates of B. There's my R vector. So let me show you how that works. So F is just negative 16j, and for R equals, in this case, BC. So we take the coordinates of point C. We take the coordinates of point B. And we get 30, negative 10, 0. So R is RCB, which in this case is 30 times I minus 10 times J. And if you need some practice, therefore, M16 is R cross F, so there's our cross product. Expand it out. Our J. Our K. And what happens when we check this out? What do we get? 0, 0, and then here, 30 times negative 16 is negative 480. So negative 480 minus 0 is negative 480 inch-pounds times K. And by golly gosh gee, look at that. That's the same thing we just got, right? So personally, I think that whenever possible, we should try and develop our vectors by, or our moment vectors by observation, because I think it's just faster, right? Now, that doesn't mean that's always going to work. So, for example, those two vectors that are kind of on that oblique plane, I think we're just going to have to surrender to the cross product on that one. But maybe for our other force couple, the one that's rotating about that other axis, maybe we can do a little bit of observation about that. Does that make sense? Everybody okay with that? All right, any questions? Okay. All right, so let me organize my calculations a little bit. So we will sort of like do that, just so that's kind of partitioned a little bit. Okay, now let's scroll up back to the back to this a little bit. I'm going to erase my little scratch calcs right here, just so this is kind of clear. Okay, so we've handled the moment generated by this 16-pound force couple. Let's deal with this one, this 20-pound force couple. Remember, the magnitude of this force and this force right here is 20 pounds. Okay, now let's ask the same question that we asked in the previous observation approach. So first off, about what axis is that 20-pound force couple causing rotation? The Y, right? Because we're yanked, so I mean, here's the prism or the box or what have you. We're pushing like this, and it's rotating about that Y-axis. So our vector is going to be some pile of junk times J, right? Second question, does our rotation follow the right-hand rule? Yes, right? Because the rotation is going to rotate like this, and if our thumb or if our fingers are rotating in the direction of that moment, our thumb points up, right? And our thumb is aligned with the positive y-axis. So do we generate positive rotation? Yes, right? So finally, what is the moment arm? What is the distance from this to this? Say again? 30 inches, exactly right. So let me write those, let's write those down. Let's write those down. So 20-pound so method one. Rotation about, pen's getting away from me, hold on. We have rotation does follow the right-hand rule. I.e. positive. And the moment arm also equals 30 inches. So FD is 20 pounds times 30 inches. I can do that math in my head. 600 inch-pounds. Usually I need to surrender to the Casio FX115 ES Plus, but this one I can do in my head. So M20 in this case is now positive 600 inch-pounds times J. Let me stop for a sec. I want to see if that makes sense. If you see the visually, if you see what's going on with this one. Yes.
So the moment arm just has to be in between axis of the lines of action? It doesn't have to be directly between the 2 points.
No, yeah, it's the shortest distance between, right? So that's, okay, so if you have some, see, that's sort of the beauty of the definition, right? So imagine here's a line of action and there's a force, right? And here's a line of action and there's a force, right? Now, the vector, the cross product needs to point from one point to another, right? But it doesn't matter which R vector you use because you end up getting the same answer, right? The reason that you get the same answer is this, right? I could define, you know, like that distance, right? I could define that distance or that distance, but I posit that there is only one line that defines the shortest distance from line to line. And it's that perpendicular distance between the two. And that's why when you take the cross product with multiple iterations of R vectors, you only get one answer because the cross product baked into that is representing that the magnitude of that cross product is equal, remember, to that area of that parallelogram. And remember, the area of the parallelogram doesn't change how much you shear it. Does that make sense? Let me pull, I can't, I'm not that good. It's easier to show. This is good stuff, though. Wait, wrong one. This is important. I can take a second. See, remember with this dimension, or this animation, right? The magnitude of the cross product doesn't change if your R vector rotates, right? Because within the magnitude of the cross product is baked that the magnitude of the cross product equals the area of that parallelogram. So it doesn't matter which way R points because that height doesn't change. Does that make sense? Everybody else okay with that? That's why it doesn't matter what R vector you use, you get the same answer. I can't draw that, so I just surrender to the technology. All right, any other questions? This is great stuff. Okay, now for the 40-pound force couple, I'm sorry, I think we kind of just need to surrender to method 2 on this one. For, I think, a couple of reasons. One is that what's your axis of rotation? It's not easily identifiable like the others where, oh, it's about the z-axis or about the y-axis. It's about, I don't know, whatever that axis is, right? So I think we need to do that calculation, but also we need that shortest distance. And that shortest distance is not, I mean, we're going to need to do, you know, the trig to figure out what that shortest distance is. And I think that in the end, we might as well just surrender to the cross product anyways, okay? So the way that I'm going to handle that is I'm going to pick a point of reference. So I think I'm going to do the same thing. All right, so let's see. How do we want to handle this? To me, it doesn't really matter. Let's be different about it, okay? So let's say that this is our point of reference. Okay. Now we need, first off, we need the force vector, right? And so if our point of reference is along the line of one of the forces, then the other force, that's going to be our force vector. Okay? That's the force vector. As for the R vector needs to start here, which is on the line of action of this force. So we could have had this or that as our point of reference. Probably didn't really matter. And it needs to end on the other line of action. So it either needs to go from here to here, or it needs to go from here to here, or anywhere in between. I don't know. Let's let's just have it point here. Again, it could point to the other one, doesn't really matter. Does that make sense? that I'm kind of just picking a point to go towards, right? Because think, this is the line of action of this one force. This is the line of action of the other. And so R just needs to start on this line and point to this line. So I could have gone from here to here, or here to here, or here to here, or here to here. It doesn't really matter, right? I just need to pick one. And so how did I pick that? A proverbial coin flip. It doesn't really matter. Also, I don't think we're going to get super significant advantage from any of them. Like, I don't think we're going to get a whole lot of zero terms out of them anyways. Okay. So let's see how we're going to do this, because I don't want to try and scroll up and down too much. So for the R vector, I'm going to take the coordinates of B minus the coordinates of D so that I can go from D to B. That's going to be pretty easy. And then for the F vector, now the F vector is going to take a little bit of work, right? Because I'm going to have to get vector BA, then I have to convert it to a unit vector, then I'm going to have to multiply by its magnitude, then I'm going to have to do the cross product, right? So it's a little bit of work to do this, this last one. So let's see if we can speed that up a little bit. All right. So if you need me to scroll back up, you tell me, okay? All right. So first thing we're going to do is the position vector. All right. So what we're going to do is we're going to get that vector right here, right? So DB, so we're going from D to B. And so the way that we do that is we take the coordinates of this point, the coordinates of that point, subtract them, and we get and so that's our R vector. Because that's the order we did the subtraction in. And please, if I'm going too fast or if there's anything that you're missing in terms of the details, you stop and you say, Dr. Mike, what the heck are you talking about? So again, we're going from D to B, and I mean, look at the vector, negative 15i, 10j, negative 10k. How do we get from here to here? Well, we go negative in the x-axis, positive in the y, negative in the z. So, I mean, those values should make sense, okay? Everybody with me on that? Okay. Now, for the force vector, and this one's going to be messy, I'll tell you. But again, I don't think that should be all that surprising because of the fact that it's on that weird angle. Okay, so we're going to need that vector, right? And in order to do that, we take the coordinates of A, which again, we've already determined all these coordinates, and the coordinates of B. Subtract them. Right? So that tells us what BA is. And again, that's in inches. Well, we need a force vector, right? So how do I get a force vector from a distance vector? I got to take that, convert it to a unit vector, multiply it by its magnitude. So let's handle that. So determine the magnitude of this. All right. And given the time frame, since we're running out of time in the class, I'm going to go ahead and give you this one. This one ends up being something like 22.361 inches. That should be pretty familiar, or should be pretty straightforward. Not familiar. And then convert that into a unit vector. So 0I plus negative 10 over 22.361 J plus 20 over 22.361 K, which is 0I minus 0.447 J plus 0.894 K. Is everybody with me on that? And then we take that, multiply it by its magnitude. And so we get F is, and again, kind of messy, but 0I minus that, and then plus and that's going to be in pounds. So now we have an R, we have an F, we can cross them, right? So R cross F, and I think by now you all should be pretty comfortable with doing that. When you chug that out, we get the moment vector, which is R B slash D cross with F. When you chug that out, you get M equals this. And that's in that. Let me take a second. Am I going too fast on that? Does that make sense? This is just me taking that R vector and that F vector and crossing it. And once you chug it all out, this is what you get. We can go through it if you'd like, but I mean, I think by now you all are pretty comfortable with cross products. So. Good? All right. So the last thing to do is to sum these vectors up. And the way that we handle that is just the way that we've added up vectors this whole time. All right. So what do we have? We have 178.89 plus 536.66 J plus 268.33K, right? But what was M20? M20, if I remember correctly, M20 was 600J. Is that what it was? So we'll just put that right there. And then what was M16? It was negative 480K. So we'll just put that, I don't know, right there. And just sum these up. And we'll call it the total moment is 178.89I. And then plus 600 in that's going to be that. And then this, we got to do some subtraction. And it ends up being negative. There we go. And so from that, if you would like, you could say, okay, what is the total magnitude of the moment? How would you find the total magnitude of the moment? Pythagorean theorem. How do you find the direction of the moment? Turn that into a unit vector, inverse cosines to get cosines about the x, y, and z axis, or the angles about the x, y, and z axis. Again, no different than what we've done before. So again, what I've done is I've taken those 6 forces on that problem and turned it into that, just a single vector. I know it took a lot of work, largely because of that one vector that was just, or that one tuple that was just kind of messy. But we've taken those 6 vectors and collapsed them into this. That's a lot easier to manage from an analyst standpoint, because we don't have 6 forces, we only have 1 vector. Does that sound good? Any questions? I'm going to pull up the code for anybody to scan in case they came in late. That's all I've got. Everybody have a wonderful weekend. Try and stay warm. I will see you all on Monday.